In the first chapter, we focused on importing data from Grasshopper into RFEM. And in the chapter 2, we are going to do the opposite, which is importing data from RFEM into Grasshopper. And for that, we are going to be using the getData component. So this component works very similarly to the setData component that we already saw, but there are some differences. So for instance, we can choose which kind of data we want to import into Grasshopper, and to do that, we have to use a boolean. So in this case, let me use a toggle, and I'm going to try to import, in this case, let's say the members and the surface to start off. And of course, in order to execute this component, since we are interacting with RFEM, we have to set this parameter to true. But because we just want to execute this parameter in very, let's say, punctual situations, we are going to use a button instead of a toggle for that. But before clicking on this button, we have to take care of two things. First, that we have one RFEM model which is running, and please take care that there is no other RFEM application running, because perhaps if that was the case, Grasshopper would try to connect to that other application, and perhaps there would be some empty models there, which would cause an error here in this component. And the second thing that you have to take care of, and we already said that at the very beginning, is that you have to start both Grasshopper and Rhino not as an administrator, so as a normal user in Windows, otherwise you would get an error. Okay, so let's say that we want to import the members and the surfaces, so let's click on True, and now we are ready to click on the button to run the import process. So now it should be ready, and we can see if we left the mouse over the members out parameter, that we have our RFEM objects here in the output parameter, like that. Okay, so now before I start analyzing our imported elements from RFEM, let's take a look at these advanced options, because of course you can also specify the name of the model, but this doesn't need to be the complete name of the model. It just needs to be something as some string text that is included into the model name. In this case, if we set this model name parameter to get, it will work anyway. Okay, like that. So of course we also have the filter, which we will take a look into it later on, and we can also import load data and load cases and load combinations. But let's go step by step. So we have our members and surfaces here, and as we said at the very beginning, what we can do is to display the information of these objects inside of a Grasshopper panel, like that. So these are our members, and we can see that we have our indexes attached to these objects already. We have our weight, we have our properties regarding cross sections, and basically anything else. Backlink length as well, so you can see that there is a lot of information here, and we have that for each member of our RFEM model. Perfect. But since this information is perhaps a bit difficult to process, what we can do is to disassemble these objects with our RFEM component. So in this case, let's get the RFEM member component. Where are you? Here it is. And what we have to do, of course, is to change the assemble options here into disassemble. So if we do that, now we are ready to plug our member object into this Grasshopper parameter, like that. Okay, so here we go. And now we can see that we can access all of these parameters quite easier, I think. So for instance, we can see the type of its member that we are importing. We can also see the numbers. So for instance, we can see in this case that the member number 2 is a RIP type member, and so on and so forth. Okay, and of course that's very interesting, but from these parameters there are some of them that I want to point out. For instance, we can directly get the weight of our members, which is I think a very interesting parameter to get information from. And also we can get the geometry. So for instance, usually the first parameter of this disassemble component is the runner geometry attached to them, if they have of course if they are related to geometry. And what we can do, of course, is to display this geometry by using a curve parameter. So let me show right now. And now we can see that we are importing the geometry of our member objects. Here it is. And perhaps I should hide the grid of Rhino. And there you go. Okay, so these are my members. And now we can do actually the same with our surfaces. But instead of using a disassemble component, let's imagine that I just want to get the geometry of the surfaces. So what we can do is to directly cast our RFEM surface objects into a surface geometry parameter. So if we get our surface parameter here from the parameters tab in Grasshopper, and we put it here, we can actually directly cast our surfaces into geometry like that. So now you can see that we are getting the geometry of our RFEM model into Grasshopper, and of course openings are also supported, and rounded openings, and so on and so forth. And curved members are also supported in case that you are interested. So this is a very perhaps a more simple approach in case that you don't need all those other parameters from our RFEM objects. But of course, if you try to use this kind of casting process, you have to take into account that it also works with similar objects. So for instance, we can cast RFEM surfaces into surface parameters, but we can do the same. We can't do the same, for instance, with members, because of course members don't have nothing to do with surfaces. But of course, we can cast members directly into curves like that. Okay, and besides geometry types, we can also automatically get the indexes of our RFEM objects by casting them into the integer parameters. So for instance, so now you can see that this is another a very basic, a very fast option or way to get the index of our RFEM objects, to directly cast them into an integer parameter in Grasshopper. Alright, so let me put it here, and the last option to analyze these objects would be to use an RFEM parameter. So if you go here to the left side of our plugin components, you have the RFEM parameter. So if we get it into Grasshopper, we can see that we can store RFEM objects here. And of course, this can be interesting to keep our definitions, Grasshopper definitions, as clean as possible. But we can also internalize the data here, which means that we could save a complete RFEM model inside of these RFEM parameters. So inside of Grasshopper, basically. And that might be interesting. Imagine in case that you have a very big or huge Grasshopper model and you are going to import it into Rhino or Grasshopper. So if you save all the objects here, you don't have to do the import process like every time that you want to work with that model, or any other application that you might find useful for these RFEM parameters. Okay, so we have been importing model data so far into Grasshopper, but as we were saying, we can also import load data or even load cases and load combinations. So let's take a look how this works. And of course, what we need to do is to set these options to true. In this case, let's try to analyze the load cases and load combinations. So let's set these items to true, and let's run the component once again. Okay, so now I should be getting this information here into this output parameter, load cases and load combinations. Okay, so it seems that we are getting this information, and of course we can display the objects parameter inside of a Grasshopper panel like that. So these are my load cases, and I can see self-weight set to 0 or to 1, and so on and so forth. And of course the same with the load combinations. But as we did with our members, we can also analyze those properties using the disassemble components. So let's try to get, for instance, the load combination component into our Grasshopper definition. And now let's set it to disassemble. and we just need to plug our load combinations here into this component, and we can properly analyze it. Because of course now we can, I don't know, display the description of these RFEM objects, but in case of the load combinations, for instance, can be very interesting to analyze if we have already defined all the interesting load combinations into our RFEM object. So for instance, we can compare the node number, the combination number parameter with the definition. So in this case, now we are seeing which are the definitions of the load combinations that are already in our RFEM model, which I think this can be very interesting for analyzing an RFEM model. Okay, so that was about the load cases and load combinations. And before finalizing this video about getting data into Grasshopper, I wanted to talk about the nodal supports. And why specifically about nodal supports? You are going to find that out in just 1 second. So now I should be getting my nodal supports here because I have already set this parameter to true. And let's try to analyze the properties of our nodal supports that are defined into RFEM by using the nodal support component like that. And let's plug our nodal supports here, but of course we have to set it to disassemble. So let's do it. And now we can see that we are getting the information of our nodal supports into these components. And of course we can analyze the degrees of freedom of our nodal objects. We can compare it to the numbers of our nodal supports. So for instance, we can say which degrees of freedom are locked, in this case the translations, or which of them have a certain stiffness, or which of them are totally free. But particularly important, and that was the reason for actually getting this nodal support component here, is the node list parameter. So let's take a look into it. And as you can see, of course, this node list parameter means the nodes to which this support type is attached. So for instance, we can see that the nodal support number 2 and number 3 is attached to just one node into RFEM, but the node number 1 is attached to several nodes. And we can also see that information in RFEM. So let's get to nodal supports, and there we go. But I wanted to point out that this list uses a very particular format, which is 5, and then 9 minus 14 to specify the nodes that this support is attached to. And of course, you can understand that because you are humans, but for a computer, that can be very difficult. So for that reason, I have created an additional parameter in Grasshopper to properly analyze this kind of list formats. So this component is this one here, the list data component. So if we get into Grasshopper, we can see that the input parameter must be a text or a string, and we now can basically plug this node list here, and what we get as output from this parameter is the same list, but now you can see that we have deconstructed it so that we can properly process it with other Grasshopper components or in another way that we want. So now we can see, for instance, that the first list has been broken down into 5, 9, 10, 11 until 14, like this list specifies. And of course, this is a property that belongs to our nodal supports, but also we can find this kind of a list format in another components like line supports or even loads, as we were seeing before. So to sum up, this kind of a list data component can be interesting when analyzing these RFEM lists that are present in several RFEM objects, as we have just said. All right, and these are our this is our node list properties. And to finalize talking about our nodal supports, let's take a look into the location output parameter. So you can see that this output parameter is not a point, although of course we can cast it into a point, and now we can see where our nodal supports are. And by the way, if you take a look here, you can see that this parameter has a tree structure because the first support is attached to actually 7 points, not just one. So this was the reason for defining it as a tree structure. So the first branch would be of course the support number 1, who has these 7 items. Okay, or which has. But this is interesting, but I wanted to explain that this is not a point parameter, but a plane parameter. Okay, so why is the reason for using a plane parameter? Let's try to explain that. So now if we get this kind of a plane parameter, we can see the supports into RFEM as well, but now, besides of getting the location, we are also getting the orientation of our nodal supports, and I think this is interesting because we can see that we have actually 7 supports that have like a normal vertical orientation, like most nodal supports, but we have these other point supports here that have a certain inclination. And let me just point out that this way of getting this orientation as a plane is very straightforward and actually very intuitive, because if you try to define a rotated nodal support into RFEM, actually you will see that you have to manually introduce or specify the angles here in these text boxes, which can be very complicated because also you have to take into account that these angles are the so-called Euler angles, so you have to specify one after the other. So trust me, this can get very difficult. So in my opinion, it is way simpler to define, to analyze these orientations through these plane parameters, and of course we can also define nodal supports, let's say oriented or rotated nodal supports, by specifying a particular orientation, which I think it can be a very interesting option. So that was basically everything regarding getting data from RFEM into Grasshopper.